Hi, my name is Anthony Rizzo, and today I'm going to be giving my lab report over Physics 2212 Lab 4 DC and RC circuits. So the purpose and goal of this lab was to predict the behavior of circuits containing resistors in series and in parallel using multimeters to measure the actual values of conventional current and potential differences in the circuits and to examine the behavior of ohmic resistors and capacitors. A quick preview of the results was that the values calculated in this experiment matched the predicted theoretical values with a very small degree of error. Some of the key concepts that we're going to be using throughout this lab include energy conservation, current conservation, circuit rules, primarily the loop and node rules, Ohm's law, resistor capacitor circuits, time dependence, resistors, capacitors, batteries, voltmeters, and ammeters. So these are some of the relevant formulas. Some come from the previous slides, such as the loop rule, node rule, and Ohm's law. I've also included some other ones, such as potential difference of a capacitor, capacitance of a capacitor, and the one for calculating the RC constant, which was found in the lab document. So to start off the experiment here, we have a series circuit that we were to produce with the constraints shown. So with that circuit, there's a diagram on the right. So we were to first find out or calculate the predicted current, which is I equals V over R, which we found just by dividing the 3 volts by 147 ohms. Next was the actual experimental current value, which was shown, which matched the predicted current. When we reversed the ammeters, the current did not change. And when we replaced one ammeter with a voltmeter, it came out to be, it read a voltage of 3 volts, and it was an open circuit, so no current will flow through the voltmeter. So next, we calculated the potential differences around the circuit, and the only segments that had a potential difference that was non-zero was between B and A, D and C, and F and E. Um, Next, using the loop rule, we were able to calculate the sum of potential differences around a closed circuit, which should equal 0. So some of the questions, why doesn't the ammeter reading change when you attach the voltmeter? That is just due to the high resistance of the voltmeter. Little current flows through, so that caused the basically a negligible change in the readings. And then what would happen to the current through the ammeter if the voltmeter is replaced with the ammeter in parallel with the 100 ohm resistor? The current will increase from 0.02 amps to 0.06 amps. This is simply coming down to the equation V equals I times R. Since the resistance decreases, the current must therefore increase. Next, we calculated the resistance at the 47 ohm resistor, the 100 ohm resistor, the wire, and the ammeter. All right, so next, moving on to the RC circuit, we were going to construct a circuit with the following constraints. So as you can see here, the first question, what happens to the bulb when it was connected to the battery? It becomes very bright and slowly becomes dimmer over time. This is the same result as when connected to the capacitor. What happened to the current in the circuit for both of the previous scenarios? So the current is initially at its greatest, and over time it decreases until eventually reaching 0. That is when the bulb goes out. And then we measured the time taken to charge and discharge the bulbs. So then we created a new circuit with the following constraints. And then we took voltage versus time data with the included features, and then we plotted them here. In the graph you can see on the right shows the natural log of potential difference over the initial different voltage versus time. So with our calculations, we found the slope of the graph to come out to negative 1.67. So using this, we can find our RC constant by saying negative 1 over RC equals the slope. So we found that there was only a very slight difference from the expected value of RC, which was 6. So the observed error was very small, and this is likely because we were using an ideal model. So any error must have come from user error when possible mistakes with measuring values and such. All right, finally for the reflection questions, if you're doing this lab in real life and use an actual ammeter instead of an ideal simulated ammeter, what's different about a real one? Basically, in real life, real ammeters have resistance, and so do all the other parts. So the measured current would be lower because it would not be an ideal situation like this lab was. And what if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistance? How quickly would our ideal model predict? So full charge in our model is achieved immediately because there's no resistance. However, in real life, it would take quite a bit of time to fully charge due to the resistance in the components. In conclusion, the node and loop rules are helpful with calculating the properties of our observed circuits, and current and voltage are time dependent and decrease exponentially around a circuit with capacitors and resistors. Thank you.